Welcome to video 5 on the TTB course. This video is from part 2 of the TTB course. In part 2, from video 3 to video 10, we consider various techniques that form the foundation of reliable TT systems. In this video, we consider effective techniques for interacting with peripherals in a TT design. The material in this video is based on Chapter 5 in the ERES2 book. If you haven't yet read Chapter 5 in the ERES2 book, I suggest you stop the video now, read the chapter, and then come back and watch the video again. First thing we're going to consider is the process of checking preconditions. Here's a simple example. We have a heartbeat task and we include in it a duplicated variable. As we discussed in the previous video, so we check the integrity of the duplicated variable. If there's a problem with this duplicated variable, then we force a processor shutdown. This is not the only problem that might arise. Suppose that the heartbeat init function has not been called before the heartbeat update task is released by the scheduler. So suppose we've not set up the port pin correctly before we call the heartbeat task. In these circumstances, the task will not detect the problem. It will run as scheduled, but the LED won't flash. Alternatively, suppose that another task in the system reconfigures the port pin that is used by the heartbeat task. Again, we may not see the heartbeat LED flashing. Neither situation may seem to be particularly serious, but they're symptomatic of a potential problem that is much more significant. Suppose that you've got an emergency stop mechanism in your system. So it might be a test vehicle that has a big emergency stop red button on the dashboard. Suppose that the emergency stop mechanism is disabled because port pins have been reconfigured by a different task. If we only detect this situation when the emergency stop operation is required, then this may have fatal consequences. If the emergency stop button doesn't work, somebody may be killed. If the emergency stop button in a factory doesn't work, somebody may be killed. How can we avoid such potential problems? An important precondition for any tasks that involve inputs or outputs is to check every time the task is executed that the relevant pins have been configured correctly. So here's another version of the switch heartbeats update task with a switch input. So we start our precondition checks, and in this case failure of any precondition will force a shutdown in the design. And again, as before, you may wish to adapt this behavior to match the needs of your particular application. First thing we do is check the static variable that's storing the heartbeat LED state, and we then perform a check of all the register configurations. In this case, we're performing a check of all GPIO registers in the design. If you have a look at TTRD205A, you will find all of the code for this example. So the code comes from TTRD205A. So what do we do if we detect corruption of a register? So we find that a port pin we were expecting to be configured in a particular way is not configured in that way. By default, we will shut down the processor in which we detect the register corruption if such problems are found. The reasons for doing this are essentially the same as those we discussed for duplicated variables. You'll find this in the ERES2 book, Chapter 4, Section 4.2. The alternative actions that are discussed in Section 4.2 and in Video 4 can also be considered here if we find register corruption. For example, we can consider performing a same mode reset. On this course, we take the view that we need to be able to detect what we call unintended peripheral state changes. Again, that definition is in Appendix 1 in the ERES2 book. This means that once a particular peripheral has been configured for use in a given system, we need to be able to detect situations in which this configuration is changed during the system operation in a manner that was not intended. For example, because of electromagnetic interference or because of a software bug. And the process is the same for all registers. We take a copy of the peripheral register settings when the component is configured. We then check this configuration regularly and frequently during the system operation. Where possible, we would aim to check the register configuration every time the peripheral is used. So as I noted previously, if you have a look at TTRD205A, you'll find an example, complete example illustrating ways of checking the register configuration. There are other matters we need to consider with peripherals, including the need for peripheral timeouts. Here's just a couple of examples. Here we're waiting for a switch pin to be released. Here we're waiting for an analog to digital conversion to complete. You probably wouldn't wait for a switch pin to be released in a TT design, because that would have very unpredictable behavior if the user kept a finger on the switch button, or if it was used in an automated system and the switch was damaged. We'd have a very long worst case execution time. You might well use some code like this in a TT design, waiting for an analog to digital conversion to complete. There's some real dangers here though. We get very unpredictable behavior if the peripheral is configured incorrectly, and we get unpredictable behavior if the peripheral is damaged. Here's a simple solution, a loop timeout mechanism. So we set a timeout loop to have a value of 0, and while we wait for some test condition to complete, and while that test condition is set to 0 and our timeout loop is not equal to 0, we wait. So eventually our test condition will be met and we'll exit from the loop. So eventually, if the test condition is not met, our timeout variable will cause us to leave the loop. This is not precise. It has to be rechecked for each system. The time delays will vary with compiler optimization settings, etc. But this kind of timeout loop mechanism is better than having no timeout mechanism at all. Here's another simple example. Here we're using a hardware loop timeout. So we're setting, in this particular example code for this particular hardware, we're setting our timer hardware to trigger set a flag. TF0 is set after approximately 10 milliseconds. So we wait in this case for our analog to digital conversion to complete, for up to 10 milliseconds. That's a very long time for an ADC conversion, but it's simply meant to illustrate the basic point here. So this time our loop is protected. It's no longer a potentially infinite loop, in that now if the A to T conversion is not completed in time, we will have a timeout flag set, and we will have a means of exiting this loop without causing a direct task overrun and potentially a direct system shutdown. So many peripherals need timeout loops of some kind of timeout mechanism when they are employed. On this course we'll consider three different forms of timeout. A task timeout, which usually involves a hardware timer. So that's a hardware timeout. Again, it's a defined term from Appendix 1. We'll also use sub-mode timeouts based on the use of a processor task. We'll talk about those in video 8. Finally, we'll use processor timeouts based on an internal watchdog timer or a similar mechanism. These are usually designed to trigger in the event of a scheduler failure or some form of unspecified fault. We will say a little more about those. We've already discussed the use of watchdogs in this way, and we'll say more about these in some later videos as well. So far in this video we've talked about mechanisms for checking that our registers have not been corrupted. We've talked about mechanisms for ensuring that if we use a particular peripheral, we can perform a timeout check when we access that peripheral to make sure that it's operating as we would expect. We also need to consider I/O sanity checks in many cases. Suppose that we wish to read an analog input value. If we follow the steps that we've outlined so far in this video, we should have configured the required ADC correctly and obtained a data sample without timing out. We may now need to perform a sanity check. For example, we may need to read from two different sensors and compare the values. Alternatively, we may need to read from the same sensor twice. Alternatively, we may need to check the rate of change of an input value. If the values change very quickly, is it possible that the real-world event that is being monitored could really have changed at this rate? In some cases, filtering may be required to remove noise from an input signal, and an out-of-line input value in an unfiltered input may be simply a symptom of such noise. Here's another example. Suppose our system is supposed to move this actuator from this position to an upright position to a position indicated on the slide with the dotted lines. Suppose that's what's supposed to happen. We need to check, we need to have a mechanism in many situations for checking that our code has triggered this movement. What sensors have we got? What confirmation have we got to indicate that this movement actually really happened in the world? Not simply that our code was correct, but that this actuator mechanism responded correctly to the instructions that we gave it, and that the correct output has been generated. In many situations, we will need to perform such a check. For example, if we're lowering the undercarriage on an aircraft, there are lots of checks we would need to perform at various stages during the lowering of the undercarriage to confirm that each part of this process had completed successfully. Very simple example. Suppose we've got a heartbeat LED function. is our heartbeat LED. We've talked about various configuration checks that we've carried out to make sure the registers are correct, to make sure the static variables are correct. We could consider adding some form of light-dependent resistor or some other form of light sensor to confirm that our heartbeat LED was operating as we expected. In most designs, this would be overkill. This would be more than would be sensible or necessary to meet the needs of the application. However, if this wasn't a heartbeat LED but was part of the LED lighting system in a car, then we would expect to have some kind of sensors that would allow us to determine that, for example, the brake lights were not working correctly or that the indicator lights were not working correctly. Such checks would be sensible and would be useful, and we would expect to include them. So these are higher level tests that typically require additional hardware as well as additional software processing in the system, but they need to be considered in many designs. That brings us to the end of this video. Before you watch the next video, please read Chapter 6 in the ERES2 book. Thank you for watching this video.